Welcome to Math with Professor V. Today we're going to practice two real AP Calculus AB free response questions on accumulation of a rate. These are the kinds of problems where you're given a rate, maybe from a table or a function, and you have to use an integral to find out how much has accumulated over time. These questions show up almost every year on the AP exam, so if you know how to set them up correctly, you can pick up a lot of points. Let's jump into the first problem. This one is from 2023, question number 1. And for the questions I'm going over today, a calculator is required. Okay, so we're given a table here. T is being measured in seconds. And then F of T is gallons per second. So let's see what it represents. It says a customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function f, where f of t is measured in gallons per second, those are the units, and t is measured in seconds since pumping began. Selected values of f of t are given in the table. So we don't have an actual equation, right? We don't know what f of t is equal to explicitly. All right, using correct units, interpret the meaning of the definite integral from 60 to 135 of f of t dt in the context of the problem. And then the second part says, use a right Riemann sum with three subintervals from 60 to 90, 90 to 120, and 120 to 135 to approximate the value of that definite integral from 60 to 135 f of t dt. Okay, so first let's focus on interpreting the meaning of this definite integral in the context of the problem. And what's really helpful is to identify what the units are of that definite integral. So let's think about it. 60 to 135 f of t dt. Well, I know f of t has what units? What is it being measured in? They told me in the problem. F of t is measured in gallons per second. So f of t is in gallons per second. Then when you're integrating, you're multiplying, right? By little increments of dt delta t. So what is t being measured in? T is measured in seconds. So if I take the product of gallons per second and seconds, notice, just good old dimensional analysis from chemistry. The seconds cancel out and I'm left with gallons. So that should be already a clue as to what this definite integral represents. It represents number of gallons, right? The total number of gallons of what? In this case of gasoline, pumped into the gas tank. And be careful, let's be specific because the definite integral had limits 60 to 135. So pumped into the gas tank from when? Those limits represent when t is 60 seconds to t is 135 seconds. Good? Okay, so whenever they ask you to interpret the meaning of some quantity, identifying the units is super helpful. All right, next they want us to use a right Riemann sum with these three subintervals to approximate the value of this definite integral. So remember, when you have a definite integral, graphically, it represents the area underneath the curve of f of t on the interval from 60 to 135. So if we're using a right Riemann sum, we're going to make three rectangles, each of whose base is given here by the difference, right, the length of the interval. And then the height is going to be determined by the function value at the right endpoint, the right endpoint, the right endpoint. Why? Because they told me use a right Riemann sum. Okay, so here we go. The definite integral from 60 to 135 of f of t dt is going to be approximately equal to rectangle number 1 will have a base of 90 minus 60 times a height of f of 90. I'm choosing the right endpoint of that interval. Plus rectangle number 2 will have a base of 120 minus 90 times f of 120. Plus rectangle number 3 will have a base of 135 minus 120 times f of 135. Okay, then clean up from here. So this is going to be 30 times f of 90. Where do I get that from? Don't have a panic attack. They gave it to us right here in the table. f of 90 is 0.15. Okay, perfect. Plus 120 minus 90, that's 30, times, now I need f of 120. Come over here. Ooh, 0.1. Beautiful. Plus 135 minus 20, 15. F of 135, of course they gave it to us. They wouldn't leave you in the lurch. 0.05. Okay. Put all this in the calculator. 8.25. Beautiful. Did they say to include units? No, just use the Riemann sums to approximate that. Great. Okay, shall we move on? Let's do it. Must there exist a value of C for C between 60 and 120 such that f prime of C equals 0? Justify your answer. So this is asking us to use the mean value theorem. Now, in particular, because we have that f prime of C is 0, really it's a specific case where we're using Rolle's theorem. If you need a refresher on that, I have a video lecture dedicated to this topic. I'll link it in the description. But basically it says as long as f is continuous on the interval from A to B, then there exists a C that's on the interval from A to B such that f prime of C equals f of B minus f of A over B minus A. So here's the important thing to remember about the mean value theorem. You can only apply it so long as f is continuous on the interval from A to B. The way it looks like things are going, A and B should be 60 and 120. Will it turn out that f prime of C should equal 0? Is f of 120 equal to f of 60? Let's go back and check the chart here. F of 120 is 0.1. And f of 60 is also 0.1. Okay, so yeah, that'll work out that f of 120 minus f of 60 is 0. Do I know that f is continuous though? Well, they told me something else about f that can help me figure the answer out to that question. It says that f is a differentiable function. Do you see that? Now, differentiability is a stronger condition. If a function is differentiable, that automatically implies that it's continuous. The reverse statement is not true. If a function is continuous, it's not necessarily differentiable. Think about absolute value of x. We've got that cusp at x equals 0. So since they told me that piece of information, let's just reiterate it. So we know f is differentiable, and that's a stronger condition. So that implies f is continuous. Okay. Continuous where? Let's be specific. It's going to be continuous on the interval from 60 to 120. That needs to be a closed interval. So we can apply the mean value theorem, which tells me that there exists. Do you know the cool slick math abbreviation for there exists? It looks like a backwards E. There exists some number C that's an element of the interval from 60 to 120 such that f prime of C equals f of 120 minus f of 60 over 120 minus 60. And that's going to be 0.1 minus 0.1 over 60, which is 0. So yes. Okay, and technically this is Rolle's theorem. Rolle's theorem is a special case where f of b equals f of a, so we just say f prime of c is 0. But either one is acceptable, okay, for your AP test. Beautiful. Don't forget to mention why we know f is continuous. That's very important. Otherwise, you can't apply the mean value theorem. All right, moving on. The rate of flow of gasoline. Okay, so like new function, right? They're giving us an equation. The rate of flow of gasoline in gallons per second can also be modeled by G of t for t between 0 and 150. Using this model, find the average rate of flow of gasoline over the time interval from 0 to 150. Show the setup for your calculations. Okay, so remember, they're asking us actually to find the average value of a function. So hopefully you remember the formula when you're finding average value of a function on some interval from a to b, it's equal to 1 over b minus a times the definite integral from a to b of f of x dx. So how would we apply this to this particular problem? Well, G of T is the rate of flow, right? Rate of flow of gasoline. And they want the average rate of flow. So what they want is G average. That's it. So it would be 1 over, what's B minus A? Well, they told me right here. B is 150, A is 0. So 1 over 150 minus 0 times the definite integral from 0 to 150 of G of T. G of T dt. Dt's, not dx's. So this would be 1 over 150 times the integral from 0 to 150. Here's G of T, T over 500 times cosine of T over 120 squared dt. Don't forget the dt. From here, they don't need you to show any work. Just put it in your calculator and round to the appropriate number of decimal places. So 0.0959967, and then you can round this to approximately 0.096. Good? Okay, so this really didn't require a whole lot. Just for you to recognize, you need to use the formula for average value of a function on an interval. Perfect, perfect. Part D, using the model G defined in part C, find the value of G prime of 140. Interpret the meaning of your answer in the context of this problem. Okay, so let me remind you, G of T is T over 500 times cosine of T over 120 squared. Okay, so we have to find G prime of 140. Well, first let's find G prime of T, and I have to use the product rule. So here's one function, here's another function. So first, derivative of T over 500, that would just be 1 over 500, and then leave the other function alone. So we have cosine of T over 120 squared, plus, now I leave T over 500 alone, and then I have to multiply by the derivative of the other function. So derivative of cosine something is negative sine the something, right? Don't touch anything else. Times, and then I have to use chain rule. I have to multiply by derivative of the inside. I think the easiest thing is to recognize what's inside is T squared over 120 squared. So the derivative of this quantity would be 2T over 120 squared. Okay, let's clean up a wee bit, and then we can plug in 140 for T. So G prime of T is 1 over 500 cosine of T over 120 squared minus, yes, exactly. So this 2 will cancel with 500. I have 250 times 120 squared, and then I have T times T. So minus T squared over 3,600,000 sine of T over 120 squared. Boom. Okay, now we can plug in 140. So G prime of 140 is 1 over 500 cosine. 140 over 120 reduces to 7 over 6, and then if I square it, it's 49 over 36 minus 140 squared over 3,600,000 simplifies to 49 over 9,000. And then again, we have sine of 49 over 36. So just put that in your calculator. Make sure you're not in degrees. And this is about negative 0.004908, which if you round to 3 decimal places, negative 0.005. Okay, whew. Now look what they asked for. Interpret the meaning of your answer in the context of the problem. So let's go back. What was G of T? Do you remember? G of T was the rate of flow of gasoline. That was G of T. So if I just took the derivative of the rate of flow of gasoline, that's telling me the rate of change of the rate of flow of gasoline. Always match up derivative, rate of change of the function. So rate of change of rate of flow of gasoline. I know, it's a mouthful. So basically, the fact that this is negative tells me that the rate of change of the rate at which gasoline is flowing into the tank is decreasing because it's negative. So let's summarize that. I'm going to say the rate at which gasoline is flowing into the tank is decreasing at a rate of, this would be 0.005 gallons per second when T is equal to 140 seconds. Good? Okay. So notice you have to really have a strong grasp of conceptually what's going on. This wasn't like a very computationally demanding problem, right? Most of it was done in the calculator. So really you just have to understand your average value of a function, Riemann sums, mean value theorem, and how to apply them. Okay, let's look at another rate accumulation problem. This is from 2019. First free response question. Again, calculator allowed, required, dare I say. So, fish enter a lake at a rate modeled by the function e, given by e of t equals 20 plus 15 sine of pi t over 6. Fish leave the lake at a rate modeled by the function L, given by L of t equals 4 plus 2 to the 0.1 t squared. Both E of t and L of t are measured in fish per hour, and t is measured in hours since midnight. Okay, so first part asks, how many fish enter the lake over the 5-hour period from midnight to 5 a.m.? Give your answer to the nearest whole number. So E of t gives me the rate at which fish enter the lake. If I want the actual number of fish, what would I need to do? I would need to integrate E of t, right? Think about it this way. What are the units on E of t? They told me right here, it's fish per hour. Fish per hour. But if I just want number of fish, I would need to multiply by hours to cancel out. How do I make that happen? I make that happen by integrating with respect to t, by multiplying by dt. So that the answer to this would be 0 to 5, definite integral, E of t dt. And then the rest you just do in the calculator, so nobody needs to see you. I mean, this is a very doable integral, but why if you're not going to get credit for doing that, okay? So this comes out to approximately 153.45769. They want the nearest whole number. So you look here, that 4 is not 5 or greater, so you're going to round to 153 fish enter the lake from midnight to 5 a.m. Look at them go. Okay. What is the average number of fish that leave the lake per hour from midnight to 5 a.m.? So again, average value of a function. Which function? The fish leaving the lake. Oh, so they want L average, leaving the lake average from t equals 0 to 5. So 1 over 5 minus 0, integral from 0 to 5, L of t dt. Are we okay? So this is going to be 1/5 integral 0 to 5. What was L of t? It was 4 plus 2 to the 0.1 t squared dt. Well, this integral you couldn't even do by hand if you wanted. You have to put it in the calculator. And this will be about 6.059038. So the average number of fish that leave the lake per hour. I mean, I would take the time to write nice complete sentences because you're not really doing any math, right? Like, so just summarize it nicely so you have guaranteed full credit. From midnight to 5 a.m. is, rounding to 3 decimal places, 6.059 fish per hour. Good? Okay, fabulous. Now this next part's going to get a little interesting. At what time for t between 0 and 8 is the greatest number of fish in the lake? Justify your answer. Well, here's what's going on. We've got fish entering the lake. That's the number that enter the lake. And then we've got fish leaving the lake. I want to know when the total number of fish is the greatest. So these are rates. If I want number of fish, obviously I'm going to have to look at some sort of integral. But I want to see when the difference between these two is at a max. Does that make sense? Because the difference between these two is basically telling me some new function, which is capturing basically the rate of change of the number of fish in the lake, right? Some are coming in, some are coming out. So sometimes this difference is positive, sometimes this difference is negative, but it's giving me like the net rate of change for the number of fish in the lake. Okay, so what I want to do is basically figure out when is the number of fish in the lake a max. How could I compute the number of fish in the lake? So say the amount, A of t, is the actual change, right, in the amount or number of fish in the lake from midnight to t hours after. How would you compute that? I would need to integrate this function, right? But I can't have them be functions of t since my integral is going to go from 0 to some arbitrary t. So I just need to introduce a dummy variable. You could do whatever you want. I'll use s minus L of s, and then this needs to be ds. Yes? Okay, well, basically, to answer the question, I want to know when A of t is a max, right? And in particular, I'm looking for the absolute max of A of t on the interval from 0 to 8. From 0 to 8. So what we're looking at is trying to find the absolute extreme value. We want absolute extrema of A of t on 0 to 8. So if you've forgotten how to find absolute extrema on a closed and bounded interval, I'll link a video in the description. You need to find the critical values. And then you're also going to evaluate the function at the endpoints, 0 and 8. So you need the critical values for A of t, which come from looking at when the derivative is 0. Yeah, so I need to find the derivative with respect to t of A of t, which is right here. So the integral from 0 to t of E of s minus L of s ds. Oh, well, I can apply my fundamental theorem of calculus, which tells me just sub in that dummy variable, right? Replace it with t. So this is E of t minus L of t. That's the derivative. How do I get my critical values? I see where that derivative is 0, which tells me E of t needs to equal L of t. So from here, you're going to have to use your calculator. You want to figure out when is E of t, which is 20 plus 15 sine pi t over 6 equal to L of t. You could not solve this by hand, okay? And then using your calculator, you should get that t is equal to 6.20356. Now, when we're finding absolute extrema on a closed interval, you take t and your function value, and you're going to evaluate it at that critical value at 6.20356, as well as at the endpoints of the interval, namely 0 and 8. And then we're going to compare all of these function values. Again, use your calculator. And then from there, you can identify where the max occurs at. And it's clearly at the critical value. So we could say the greatest number of fish in the lake happens or is when t equals, let's round to 3 decimal places, 6.204 hours. Okay. Now there is another way you could answer this problem. You could say, look, I know the max amount of fish will be in the lake based on whether or not this difference is positive or negative. So you don't even have to define this function here. You could just jump to setting this equal to 0. Okay. And then from there, you could find, okay, t would need to be 6.20356. And then from there, you would just look at the difference, basically. Like, here's 0, here's 8, here's 6.20356. And you just want to check if f of t is positive or negative on either side. F of t is positive here, which means fish are entering more than they're leaving. And it's negative here, which means the max occurs at t equals 6.20356. And both approaches would have gotten you full credit on the AP exam. You just need to justify completely. I think most of you guys would be in calculus mode, so you might go through this process, but it involves a lot more rigor and setup. So if this kind of naturally occurred to you, go for it, okay? Both would be totally acceptable. Okay, last part of this problem. Is the rate of change in the number of fish in the lake increasing or decreasing at t equals 5? Explain. So the rate of change in the number of fish we defined earlier to be f of t, right? So f of t was e of t minus L of t, and that's the rate of change in the number of fish. And they're asking, is that rate of change increasing or decreasing? So then I need to look at f prime of t, and is it positive or negative when t equals 5? That's basically all they're asking me to do. So f prime of t would be e prime of t minus L prime of t, and f prime of 5 would be e prime of 5 minus L prime of 5. Again, use your calculator, okay? So that would be negative 10.7228. No one really cares what the number is, just so long as we say it's negative. I mean, write down what it is, but okay. And then that tells me, okay, the rate of change in the number of fish is decreasing, okay? When t equals 5. Woohoo! So if you're studying for the AP Calculus exam, I have tons of full calculus lessons and practice problems on my channel that can help you review if any of these concepts you felt like were a little murky and you needed to brush up. And if you want more AP Calculus free response practice like this, let me know in the comments. I'll make more videos walking through real exam questions step by step. Thank you for watching. I do want to point out too, I did this one derivative by hand. You could totally throw it in your calculator, okay, on this portion of the AP test, but I thought it would be good practice for us all right now. And don't forget to give this video a thumbs up, subscribe if you haven't already, leave me a comment down below if you want more AP style questions, and don't forget to follow me on Instagram and TikTok, Math with Professor V. Love you all so much. I'll be back sooner than later. Bye guys.